Hello guys, hope you're doing well. My name is Mahmoud Kiasri and welcome to the new chapter of control. As you guys remember, for the previous chapter, we were talking about the zeros and poles and how each of them was going to have impact over our system itself. As we all know, poles means they're the DNA of the system and they who do have the real impact on the steady state system. And this means that our system is going to be stable or not based on the location of those poles. And also zeros are going to have a little bit of impact over the transient response. So at this point, we're going to again talk about other aspect of those, trying to see a couple of examples and also see that what would happen if we don't consider zeros at some point or another. Without further ado, let's talk about it. So as I just mentioned before, and at this case, we are going to see that what would happen to the system that when we do have the poles and zeros, and what would happen to the time response and any other kind of factor. But for the recap, if you guys remember, every time that when we were talking about the system or our control system, we talked about specific concept that we know it as the GS or the transfer function. As I just told you, most of the system or all of the system are going to work based on the time. But we know that working on the time means that we have to deal with high number of calculations. Is going to be complicated, and especially if you do have more than one system. So on that point, we are going to talk about the S domain or working on the frequency domain. On that side, a very important thing that we have to see is what is a transfer function itself. And obviously transfer function has a numerator and has a denominator. And based on the frequency domain, we have to find the poles and we have to find the zeros. And based on that, we can understand what is happening to our system itself. We had some kind of a playground that we call it as an S-plane. S-plane has a real number and has an imaginary side. For a real number that we call it as delta, and for an imaginary number that we do have it as j omega. So based on the location of the poles that we had the left-hand side and we do have the right-hand side, we can get a very, very good prediction of what would happen to the system. Is it going to be stable or not? If all of my poles are going to be on the left side, like the system, like this, some kind of the transfer function that we do have over here, that S is equals to -1 and S is equals to -4, if both of them are going to be on the left side, which in this case they are, we can consider that the system is stable. Based on the pole, based on the zero, we can understand that what would happen to the transient location of our specific system. So as I just mentioned, the poles are going to be the drivers. They determine stability, oscillation, and speed. Left is stable, which is good. Right is unstable. And the x-axis is sustains, oscillation, which means that over here that we don't talk about it that much. Most of the time we do have the poles on the left, either on the left side or right side, and then we are going to move forward from that side. So when we do have the zeros, it means that those guys are modifiers. It means that they tweak amplitude and phase, but they never cause instability on their own. As you just know, and as we all know, and we have to remember all the time, the mapping the system DNA is something that actually poles are going to do that. So if you would like to have a little bit of comparison between which one is going to do what exactly, for the primary function, as we mentioned, the poles are going to be determined stability and baseline speed. On the other hand, zeros are going to be modify response shape and amplitude itself. It means that during the transient time. Effect on the stability, as just mentioned, zeros do not have any effect on the stability itself, while the poles are actually going to dictate the life or death of the system. For the real world analogy, the mass and springs of a car, for instance, imagine that, while the zeros enact the aerodynamics, and external forces. When we are talking about the RHP danger, it means that while your poles are going to be on the right side of the S-plane, means that it's critical fail, and when we are talking about the zeros, the warning is that the system is going to survive but behaves irrationally. So we can talk about a very, very simple example, like the cruise control scenario. Imagine that you had a system just like the last page, and after that you had two poles, S as a -2 and S as a -5. So it means that if the poles is going to, what would happen if I do have the poles that's going to move to S2 positive 0.1, is that your car is going to have accelerate uncontrollably. It means that we would like everything, or we would like the poles to be on the left side. So obviously when we are talking about the system, their poles and zeros are not the only thing that we have to consider. Another factor or some kind of a knob that we do have is going to be one of them is going to be oscillation knob, or we can call it as the zeta itself. So at some point we called it as the damping. So at this point, we would like to see that what would happen if we some kind of change this damping ratio. And damping ratio is something that comes outside of the DNA of the system itself. So what was the mechanism? What was the definition? The zeta controls how much the system resists movement. It strictly governs overshoot and oscillation itself. And the main formula for that is that the amount of overshoot, which in your show it with percentage, is going to be e to the power negative pi times zeta divided by root of the 1 subtracted by zeta to the power 2 times 100. For example, if I do have a system that its damping ratio or zeta is 0.2, its overshoot can be calculated based on that, and we do have the 2.7% of overshoot. Imagine that you have a robotic arm and it's going to swing wildly and pass the targets before it's settling. By having the damping ratio, we can understand that how much my system is going to resist against all of those changes. And based on the damping, the number that we do have, there are some kind of different conditions. The damping up to 0 means that the system is underdamped, means that it's just pure, it doesn't have any kind of resistance to any kind of changes, which we don't like it, obviously. Another one is about the damping between 0 and 1, means that the system is underdamped, and it means that the system is going to be oscillatory but decaying, which means that fast, but obviously it has a little bit of overshoot. Then we do have the zeta is equals to 1, which is critical damp, the fastest possible response without any overshoot. This is going to be one of the favorite one. And when we do have the zeta is bigger than 1, it means that your system is overdamped, is sluggish, heavy, and you have 0 overshoot. So obviously you can have some kind of different examples in your own mind, and this is the thing about the zeta, and we can some kind of change the tuning to make their system either working on underdamped or under overdamped, critical damped, or any other kind of system that we would like. The next tuning model, or the next some kind of tuning lever that we do have related to our system itself, is going to be about omega n. As you guys remember, omega n is going to rule the speed of the system itself. While if we increase the omega n, we can some kind of have the faster system. It means that it's going to reach to the response or reach to the steady state faster, while it has some drawbacks because we are going to see some kind of overshoot or instability. But still, again and again and again, the stability is something related to the poles. So whatever is happening for the transient system, it's mostly related to our zeros, while we know that our system is going to be stable at the end. So how's the mechanism? It means that omega n is going to strictly controls of how fast the system responds. So what is the rule? Omega n does not affect the overshoot, and that's going to be solely what? That's going to be solely as our damping ratio's job. So what is the formula for that? The damped frequency, or some kind of amount of frequency that we do have based on that specific damping, is going to be omega n, which we know it as about the speed control, times root of 1 subtracted by zeta to the power 2. It means that your damping frequency is something related to the speed of your system and about the damping ratio. Imagine that you do have a system that its omega n is 2. It's not that fast, it's okay, and the zeta is 0.5. And when you do have a system that is omega n is 10 and the zeta is 0.5. So what we understand that the system B is going to settle 5x faster, but hits the exact same 16.3 overshoot. What does it mean? It means that the overshoot at this point doesn't have anything to do with what? Doesn't have anything to do with your omega n. The overshoot is something completely related to your zeta, as we all remember for the previous slide formula itself. So maybe at some point you would ask your question yourself that, okay, we would like a fast system, right? But obviously not all the time the fast system is good, because fast system is going to cause some kind of increasing your band frequency, increasing your bandwidth, and after that you entered the frequency, there's some kind of the noise zone. What does that mean? It means that if you increase your omega n in order to reach to a faster system, this guy is going to increase the bandwidth itself. When you have the high bandwidth, it means that this guy is going to act like a megaphone for high frequency sensor noise, which is something that we don't like. Another thing is about the actuator saturation, because when we do the simulation, if you guys remember at the very beginning of this chapter, we talked about different kind of steps while we were trying to make a system actually. First of all, we have to do our study, then we do have the simulation, and then we have to have the implementation. While we do have the implementation on an actual physical system, we do have the constraint. We cannot do anything that we want. While on simulation, everything is good. I can increase the omega n as much as I want. I do have constraint and I do have limitation on the physical aspect. So physical motors have some kind of limits. Demanding infinite speed means that the motor maxes out, leading to nonlinear oscillation. So faster is better, works in simulation only, and it's going to fail in reality itself. So imagine that you do have a drone controller, and if you increase this omega n inside the drone from 5 to 50, at some point you say that, okay, simulation shows perfect step response. But at some point, if you do it in an actual world, the drone is going to vibrate violently in the air itself, obviously, which we don't like because it enters the high frequency zone. It means that your bandwidth is increasing, while the speed is faster, it's going to be very, very vulnerable to any kind of noise itself. Another important, some kind of batch of formulas that we had in the previous slide was about 4 important variables or 4 important characteristics of your system. The very first one was about the rise time, amount of time that it takes for a system to reach from 10% to 90% of its maximum. That is something related to your omega n. By assuming that your zeta or damping is 0.5, you do have 1.8 divided by omega n. Then we do have the peak time. The amount of time that it takes for a system to reach to its maximum is going to be pi divided by omega d, also going to be pi divided by this formula. Then we do have the settling time. How much time does it take for my system in order to reach to error of 5%, which would be 3 divided by zeta omega n, or 4 divided by zeta omega n. And finally, we do have the settling time, which is for the 2%, which most of the time we consider either of these two are either 2% or either 5%. So we do have the 4 divided by zeta omega n, and it's completely makes sense. So for an example, imagine that you do have your omega n as 4 radian per second and your zeta or damping ratio at 0.6. So obviously you can find a TP, you can find a TN, and you can find overshoot and everything, any information related to that. While we're trying to design the system, we really have to look at our limitation, especially our physical limitation. And when we are trying to design that, first of all, we have to start with constraint, then try to decide about any other kind of aspect of our system itself. Imagine that I do have a system that its requirement is that the TS or the settling time should be less than or equal to 2 seconds, and overshoot should be less than or equal to 10%. And if I would like to map the feasible region, I have to consider based on that TS and based on that overshoot. While I'm considering the overshoot of less than 10%, it means that my damping should be more than 0.6. And from the TS of less than 2 seconds means that my omega n should be more than or equal to 6.78 radian per second. And at this point, I can select and validate. It means that, okay, I chose 2 numbers, but still I have to check that this is going to be satisfy my requirements or not. And if I do the validation over here, for example, if I choose that specific number for omega n and zeta, I can find the TS itself, and TS is 0.95, which is something that is okay, and overshoot is also fine. So it is very important. First of all, start with your constraint, find some numbers, and when you found those numbers or characteristic of your system, you still have to validate them. So when we are talking about the engineering system, when we are talking about obviously any kind of system, we have to consider the trade-off matrix. It means that we cannot have anything that we want. We cannot have all of the advantages at the same time. So we do have 3 important factors in any engineering system. We do have speed, we do have the hardware, and we do have the stability. It means that if I would like to have some kind of higher amount of speed, or if I would like to compare the speed and hardware itself, decreasing the settling time by just raising omega n is going to amplify the noise and saturate the actuators. As you guys remember, if I would like to have my system to have the higher speed, obviously the very first thing that comes to my mind is to increasing the omega n, while I didn't consider the fact that my hardware also has some kind of issues and I cannot increase as much as I want. And also the other factor, the other danger zone, means that I'm going to enter the noise zone, or going to high bandwidth zone. And another point, we do have the stability with hardware itself. It means that heavily damping the system, it means that if I increase the zeta, as you guys remember, if I increase the zeta, I'm going to have the very, very heavy damping system, and that system is not going to have very good response to any kind of changes. It's going to make it stop. And it means that requiring a massive actuator effort to push the system to the target in a reasonable timeline. It means that if I would like to do any kind of changes to my system itself, I have to put so much effort, or I have to make my system so heavy, and obviously it's going to consume so much power in order to reach that specific value I want. And finally, speed with stability. It means that decreasing the settling time by lowering the zeta is going to increase the overshoot and oscillation. As you guys remember, the oscillation has highly related to the zeta itself, and if I do anything with that, I'm going to lose something. So at the end of the day, there is no perfect number or for the optimal design. It means that I have to find the exact center of this triangle for the hardware and for the hardware physical limits, and then I can move forward. So about the real number, about the complex, and about the dominant part, let's again look at some kind of the GS. As you guys remember, when we do have the poles, and those poles are going to be our real numbers, it means that my system doesn't have any oscillation, because oscillation is something related to complex poles. So it means that at this point, I do have some kind of poles are going to be only real numbers, and it's going to be pure smooth exponential curve with zero overshoot. On the other hand, if I do have a system that not only is going to have the real part, but also going to have the imaginary part, it means that my oscillation is going to be, I do have the oscillator system, and it's going to have the decay curve. But based on the fact that my poles are on the left side of the curve, on the left side of the S-plane, I can consider that my system is stable. So at the end of the day, both of them are going to be stable itself. So as I just mentioned, not all poles are going to carry equal weights. This is a very important one. If you guys remember from the previous chapter, the pole closest to the imaginary or the y-axis is something that we call as dominant pole. Imagine that you do have a system, and at that system you have two poles. One is -10 and another one is -1. The S-1 considered as the dominant. Why? Because it's closest one to the y-axis, and it is the slowest to the decay at tau around 1 second, while this -10 is going to vanish almost instantaneously because it is fast. So if we would like to see in a real example, or in a better example, imagine that you do have a system. It's going to be like this. At this point, you see that we do have 3 poles. So if I would like to put some numbers on that one, imagine that my system is 50 divided by s plus 1, s plus 8, and s plus 10. Obviously, I do have -1, -8, and -10. But how I can decide that actually in this system, which one is going to be dominant and which one is going to vanish so fast? We do have the rules of thumb. And this rule says that 5x rule. It says that if non-dominant or fast poles are going to be 5x further left than the dominant slow poles, you can some kind of safety drop them from the math itself. What does it mean, drop them from the math? It means that while we are trying to somehow simplify our system or transfer function, we just simply says that for the dominant pole, this is as the way it is, while these guys, their S is going to be 0 itself because they're going to vanish so fast. It means that at the end of the day, my T is going to be 50 divided by 80. What was 80? 80 was actually 8 times 10 itself, and is going to be divided by s plus 1, obviously. So finally, I'm going to have the system itself. So it is very, very important while we're trying to deal with poles, we still have to consider the fact that you have to take care of your zeros, because obviously they are going to have some impact. And at some points, if we are very close to your poles, they are going to have some kind of cancellation method, or you can get rid of poles based on that zero itself. So as I just mentioned, the impact of zero is related to the transient response, because the DNA of the system or poles are going to actually decide what would happen at the end of the day. Imagine that you do have the standard second order curve, so it's going to be like this with no issues, because you have a very stable condition, you don't have that much of a zeros over here, so everything is fine. And LHP means that the zero is going to be added. So at this point, I'm going to have a little bit of speed, I'm going to have some kind of overshoot penalty. So LHP means that it's going to be on the left side, I don't have that much of issue. But if I do have the RHP, or it means that my zero is going to be on the right side, is going to have the inverse response. And as you can see, instead of overshoot, I do have this undershoot itself. So what does it mean? Imagine that you do have the CNC machine, and this CNC machine has zeros on the right side. So a precision CNC machine tool has the RHP 0 at S is equals to +2. It means that the move tool right by 5 millimeter is going to make the tool physically to jerk left first, gouging the metal before reversing and moving right, which is going to be quite nightmare. It means that you're moving to the right, but at some points your robot or your So your CNC machine is going to move to the left, and again, we will have to move back to the place that it was. That's why it's not feasible. Most of the time, we care that if you do have the 0, it should be on the LHP, just like the pole itself. Everything is stable, everything is smooth. I mean, not that specifically smooth, but yet it's going to be better than this one, because dealing this guy from reaching from this point to this point is way better than reaching from this point to this one. That's why we have to care. Another important thing is that at some point you are going to forget about the 0. If you do that, you are going to face a serious issue. Why? Let's see an example. Imagine I do have the transfer function, and this transfer function is like this. Obviously, I do have 2 poles on the left side. The system is going to be stable. I do have a little bit of overshoot, and it's going to be this green dotted line like this. So if I consider that my system is like that, my overshoot is going to be 9.5%. While my actual system was like this, it means that I forgot to consider the zeros because my system was so saturated by just using the poles itself. At this point, if I do have my S plus 1.5, it means that this guy is going to do what? This guy is going to cause some overshoot. At the end of the day, both of them are stable, but overshoot is another important concept that I still have to consider for my system itself. So by don't considering that S as negative 1.5 and it's on the LHP, I'm going to lose this overshoot, and I don't consider that. Obviously, the result is not something that I would like. And if I would like to have some kind of real world test, we can considering the spring and some kind of the damper and the mass and the mechanical system, or you can consider the fact of the luxury sedan and you can the sports car. Obviously, in the luxury machine, we do have the higher zeta because we would like to reach to the stable system, not very fast, but it should be smooth. On the other hand, in sports car, speed is everything that we need, and actually is most of the thing that we care. So as you guys just saw over here, again, we were trying to focus so much on the poles and zeros and what would happen if you change them, what would happen if you forgot them, and what are the related formula to them, what is the damping, what about the some kind of speed of the system itself, and what would happen if you increase it too much. So in these chapters, I really would like to again put emphasis on the fact that when you're talking about the control system, dealing with these factors, I mean, these that the poles and zeros are very important one. For the next chapters, we would like to expand a little bit more to see that what would happen if we don't consider other kind of factors in our system itself, and how we can use actually zeros and poles to deal with anything that we do have for the system and try to make it to the specific thing that we want. Again, my name is Mahmoud Kiasari. Thanks for watching this. Have yourself a great day, night, whatever. See you around.